Good day, everyone. I'm Richante Buscato, and I will be presenting to you the Sieve of Eratosthenes for today. The Sieve of Eratosthenes. Given a particular integer, how can we determine whether it is prime or composite? And in the latter case, how can we actually find a non-trivial divisor? The most obvious approach consists of successively dividing the integer in question by each of the numbers preceding it. If none of them except 1 serves as a divisor, then the integer must be prime. Although this method is very simple to describe, it cannot be regarded as useful in practice, for even if one is undaunted by large calculations, the amount of time and work involved may be prohibitive. There is a property of composite numbers which allows us to reduce materially the necessary computations, but still, the above process remains cumbersome. If an integer a is greater than 1 is composite, then it may be written as a equals bc, where 1 is less than b, less than a, and 1 is less than c and less than a. Assuming that b is less than or equal to c, we get b squared less than and equal to bc equals a, and so b is less than and equal to square root of a. Since b is greater than 1, theorem 3.2 ensures that b has at least one prime factor p. Then p less than and equal to b less than and equal to square root of a. Furthermore, because p such that b and b such that a, it follows that p and a, the point is simply this: a composite number a will always possess a prime divisor p satisfying p less than and equal to square root of a. Testing the primality of a specific integer a is greater than 1, it therefore suffices to divide a by those primes not exceeding square root of a, presuming of course the availability of a list of primes up to square root of a. And this may be clarified by considering the integer a equals 509 and as much as 22 less than the square root of 509 and less than 23. And we need only try out the primes which are not larger than 22 as possible divisors, namely the primes 2, 3, 5, 7, 11, 13, 17, and 19. Dividing 509 by each of these in turn, we find that none serves as a divisor of 509. The conclusion is that 509 must be a prime number. Okay, so as you can see here in the screen, we have example 3. The foregoing technique provides a practical means for determining the canonical form of an integer. Say a equals 2093, and since 45 is less than square root of 2093 and less than 46, it is enough to examine the multiples 2p, 3p, 5p, 7p, 11p, 13p, 17p, 19p, 23p, 29p, 31p, 37p, 41p, 43p. By trial, the first of these two divide 2093 is 7, and 2093 equals 7.299, or maybe 7 times 299. As regards the integer 299, the 7 primes which are less than 18, note that 17 is less than square root of 299, and less than 18 are 2, 3, 5, 7, 11, 13, and 17. And the first prime divisor of 299 is 13. And carrying out the required division, we obtain 299 equals 13 times 23. But 23 is itself a prime. Hence, 2093 has exactly 3 prime factors, which is 7, 13, and 23. So that 2093 equals 7 times 13 times 23. Another Greek mathematician whose work and number theory remains significant is Eratosthenes of Cyrene in 276 to 194 BC. While posterity remembers him mainly as the director of the world-famous library at Alexandria, Eratosthenes was gifted in all branches of learning, if not of first rank in any. In his own day, he was nicknamed Beta, because it was said he stood at least second in every field. Perhaps the most impressive feat of Eratosthenes was the accurate measurement of the Earth's circumference by a simple application of Euclid geometry. We have seen that if an integer a is greater than 1 is not divisible by a prime p less than and equal to square root of a, then a is of necessity a prime. Eratosthenes used this fact as the basis of a clever technique called the Sieve of Eratosthenes. For finding all primes below a given integer n, the scheme calls for writing down the integers from 2 to n in their natural order, and then systematically eliminating all the composite numbers by striking out all the multiples 2p, 3p, 4p, 5p, and so on of the primes. P is less than and equal to square root of n. The integers that are left on the list, those that do not fall through the sieve, are primes. To see an example of how this works, suppose that we wish to find all primes that exceeding 100. Consider the sequence of consecutive integers 2, 3, 4, and so on up to 100, recognizing that 2 is a prime. We begin by crossing out all even integers from our listing, except 2 itself. The first of the remaining integers is 3, which must be a prime. We keep 3 but strike out all higher multiples of 3 so that 9, 15, 21 are now removed. The even multiple of 3 having been removed in a previous step. The smallest integer after 3 which has not yet been deleted is 5. It is not divisible by either 2 or 3, otherwise it would have been crossed out. Hence it is also a prime. All proper multiples of 5 being composite numbers, we next remove 10, 15, 20. Some of these are of course already missing. While retaining 5 itself, the first surviving integer 7 is a prime, for it is not divisible by 2, 3, or 5, and the only primes preceded. After eliminating the proper multiples of 7, the largest prime less than square root of 100 is equal to 10, and all composite integers in the sequence 2, 3, 4, and so on to 100 have fallen through the sieve, and the positive integers which remains to it 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, and have so many are all of the primes less than 100. So the table below represents the result of the completed sieve. The multiple of 2 are crossed out by, the multiples of 3 are crossed out by, and the multiples of 5 are crossed out, and also the multiples of 7 are crossed out. Okay, so as you can see in the table, so the remaining numbers here is all prime numbers. At this point, an obvious question must have occurred to the reader. Is there a largest prime number, or do the primes go on forever? The answer is to be found in a remarkable, simple proof given by Euclid in Book 9 of his Elements. Euclid's argument is universally regarded as a model of mathematical elegance. Loosely speaking, it goes like this. Given an infinite list of prime numbers, one can always find a prime not on the list, and hence the number of primes is infinite. The actual details appear below. According to the theorem 3 to 4 and from Euclid, there are an infinite number of primes. And we have this proof. Euclid's proof is by contradiction. Let P sub 1 equals 2, P sub 2 equals 3, P sub 3 equals 5, P sub 4 equals 7. Be the primes in ascending order. And so that there is a last prime, call it P sub n. And now consider the positive integer. P equals P sub 1, P sub 2, P sub n plus 1. And since P is greater than 1, we may put theorem 2 or 3-2 to work once again and conclude that P is divisible by some prime P. Got P sub 1, P sub 2, and P sub n are the only prime numbers. So that P must be equal to 1 of P sub 1, P sub 2, P sub n. And combining the relation of P such that P sub 1 and P sub 2 and that P sub n with P such that P, we arrived at this formula, or equivalently to P such that 1. And the only positive divisor of the integer 1 is 1 itself. And since P is greater than 1, a contradiction arises. Thus, no finite list of primes is complete. Hence, the number of primes is infinite. It's interesting to note that in forming the integers P sub k equals P sub 1, P sub 2, P sub k plus 1. And the first 5, namely P sub 1 equals 2 plus 1, so equals 3. And P sub 2 equals 2 times 3 plus 1 equals 7, as you can see in the screen. And next we have P sub 3 equals 2 times 3 times 5 plus 1 equals 31. And we have P sub 4 equals 2 times 3 times 5 times 7 plus 1 equals 211. And lastly, we have P sub 5 equal to 2 times 3 times 5 times 7 times 11 plus 1 equals to 2311 are all prime numbers. However, P sub 6 equals 59 times 509, and we have also P sub 7 equals 19 times 97 times 277, and we have P sub 8 equals 347 times 27,953 are not prime number. As you can see in the prime numbers below, so we have P sub 6, P sub 7, P sub 8 is all are not prime. And a question to which the answer is not known is whether there exists infinitely many k for which P sub k is a prime. For that matter, are there infinitely many composite P sub k? Euclid's theorem is too important for us to be content with a single proof, and here is a variation in the reasoning. Form the infinite sequence of positive integer. Okay, alright, so Euclid's theorem is too important for us to be content with a single proof. So as you can see on the screen is how the process of Euclid's theorem. Since each n sub k is greater than 1, each of these integers is divisible by a prime. But no two n sub k can have the same prime divisor. To see this, let d equals g cd, or the quantity of n sub 1 and n sub k, and suppose that I is less than k, then d divides n sub I. Hence, but divide n sub 1 n sub 2 n sub k minus 1. And since d divide n sub k according to the theorem of 2 tell us that d divide or such that n sub k minus n sub 1 and sub 2 dot 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 n sub k minus 1. The implication is that d equals 1, and so the integers n sub k, or the quantity of k, equals 1, 2, and that are pairwise relatively prime. The point which we wish to make is that there are as many distinct prime as there are integers n sub k, and namely infinitely many of them. Let p sub n denote the nth of the prime numbers in their natural order. Euclid's proof shows that an estimate to the rate of increase of p sub n is this formula, as you can see here. And for instance, when n equals to 3, the inequality states that 7 equals p sub 4 is less than p sub 3 cubed plus 3 equals to 5 cubed plus 1 equals 126. One can see that this estimate is wildly extravagant. A sharper limitation to the size of p sub n is given in theorem 3 to 5. If p sub n is the ninth prime number, then p sub n is less than or equal to 2 to the power of 2n minus 1. For the proof, let us proceed by induction on n, the asserted inequality being cleared through when n equals 1. As hypothesis of the induction, we assume that n is greater than 1 and that the result holds for all integers up to n. And then, p sub n plus 1 is less than or equal to p sub 1, p sub 2, p sub n plus 1, as you can see, and less than or equal to 2 times 2 squared, 2 squared n minus 1 plus 1 equals to the power of 1 plus 2 squared plus plus 2 n minus 1 plus 1. Recalling the identity 1 plus 2 squared plus plus 2 n minus 1 equals 2n minus 1, we obtain that p sub n plus 1 is less than or equal to 2 squared n minus 1 plus 1. But 1 is less than or equal to 2 squared n plus 1 for all n. Hence, p sub n plus 1 is less than or equal to 2 squared n minus 1 plus 2 squared n minus 1. So that it equals to 2 times 2n minus 1 equals 2 squared n, completing the induction step in the argument. Alright, that's the end of my discussion, and I hope you learned something from my presentation, and thank you for listening.